Okay, welcome everybody. It is a pleasure to have today Aidan Herderschee, who is going to tell us about nextly northern scattering waveforms. So, please.
Hello, thank you so much for having me. I'm going to talk about some work that has been posted, but is also ongoing with Radu Roybin and Fei Tang at Penn State. And I'm going to talk about scattering waveforms in classical gravity. We're using basically computing these objects using scattering amplitudes. So the structure of the talk is that the majority of this talk will be introduction and motivation for why I'm actually computing what I'm computing, since if you're ever doing a hard calculation, you want to have a good justification for it. The next few things will basically be some general statements about that I hope might be general lessons for everyone here about how you compute expectation values with amplitudes as a general technique, and then also how you study the classical limit in scattering amplitudes. So this is not something taught in your field theory course, but probably should be. And then I'm going to apply these two techniques, which I hope might be generally relevant for people here. It's useful in a wide variety of subjects, and specifically apply them to computing the scattering waveform. I'm then going to, and hopefully at the end, if we have time, analyze the scattering waveform and then just do a summary with conclusions. I will state that the scattering waveform has generated a lot of interest. These are all papers devoted to doing this computation in a variety of different ways. The first one is the paper with me, Radu, and Fei. That was earlier this year that computed the waveform in time domain. Then there was another paper by some people, Quinn Mary, that computed in frequency space at the same time. And then from another group that computed it, some things here, like this radiation reaction effect. And then a follow-up paper. Then there was another fourth paper over here. Then there are two papers that happened a few months after that had relevant contributions. This one by Simone, Mathieu, Hoffy, and Sebastian basically showed that these computations, at least these two, had missed one extra term in our calculation. We basically made an I epsilon prescription mistake, which we'll be adding back into the paper. So that was, this paper made a contribution by, there was a small mistake in these two papers. And then this paper is a paper by some hardcore GR people that did the computation with an additional expansion in GR directly. So they actually just solved the equations of motion directly in GR. And they didn't reproduce the full result, but the result in a particular expansion. And then they compared. They found that we were wrong because this paper pointed out earlier, we were missing a term. But there is an ongoing paper that will be published soon that will contain, one, we're going to correct our paper to include the missing term, which is not very complicated, along with some additional discussion of like actually getting some additional analytic results, and then finally comparison with the GR result. So these are, if you're interested in looking at the papers on the topic, these are the main papers. Now we get to motivation. What are we actually computing? Well, let's start super big picture. What is the field I'm trying to study? Physics is pretty big. We're studying gravitational wave astronomy. So we're in a new era where people can actually measure the gravitational waves emitted by binary black holes. And there are a sequence of experiments in the coming decades that are going to measure these with higher and higher precision. A generic binary merger has three processes that matter. The first one is the in-spiral phase, where the black holes are orbiting each other. And this is basically where you identify what is happening. Like you might, as an experimentalist, use the in-spiral phase waveform to basically search through your data set to like look for anything that has roughly this pattern. And then you will also spend studying the merger and ring down, which is when the black holes actually coalesce. So the merger is like a strong field regime. The black holes are merging together. That's this region here that's super highly peaked, very complicated. And then finally, the ring down, where you're just doing black hole perturbation theory. It's a black hole that's highly excited, and they have highly excited quasi-normal nodes. The general, as I was saying before, what you generally do, what I like to think the experimentalists do in my head cartoonishly, is that they look for in-spiral phase waveforms. And then once they find a waveform that matches the in-spiral phase waveform, they then go and apply the technology, which is much harder to actually compute the merger and ring down waveforms. So usually you have a wide variety of in-spiral waveforms, and then once you've actually identified something as being an in-spiral waveform, you then go and explicitly compute the merger and ring down waveforms. That's a cartoon. The reason that these in-spirals are so interesting is that they're really a probe of new physics. It's like fundamentally new physics. This is a very incomplete list, but I think it's really good to emphasize this because I think a lot of the times people just think this is just another test of general relativity, but there is actually like a finite fraction chance of finding like fundamentally new physics within the coming decades. Like one, this is precision test of general relativity. It's always good to test the theories that we know. Probing the strong field regime of general relativity with the merger. This is again like a regime where we don't actually know if the rules obey what we think they do. They probably do, but it's good to check. But then here we get to like really more out there proposals, like if you're of ultralight particles and you're measuring a black hole that has large extremal mass ratios, you might be able to basically measure the effect that they're ultralight particles near the horizon. You can get enhanced quantum gravity effects if you have small magnetic black holes. There's a paper by Juan. And then in addition, there are these like variety of new predictions for quantum gravity phenomena. For example, like there's just enhancement of uncertainty in quantum gravity. There's a paper by Catherine Zirk and Eric Verlinde. Like all of these are individual, more phenomenological proposals, but these are like also worth testing. Like if any of these are true, it's a big deal. Like so there's a statement here of even if you think that it's an epsilon chance that each of these individual things work out, if you have a 1 over epsilon number of things that could happen, you have an epsilon over epsilon effect, and there's like a finite fraction probability that you get new physics. So I think there's really a statement here that even if you don't believe in individual things here, just the sheer number of plausible things that could happen actually implies that we might see something new. Also, finally, perhaps the most important one is just foundationally, the statistics of the distribution of events is interesting. Like even if you don't care about the individual ring down or the individual waveforms and don't think those hold interesting physics, the distribution of binary black holes in the galaxy is just an interesting astrophysics. Like it provides interesting astrophysical information. So it's important we study this. This is like something that it's good that we learn more about. So what are the bounds? Like why didn't we do this 30 years ago? Like people like, why didn't we do this in the 2000s? Like why did we spend $1 billion on a giant particle collider instead of like building Lego 20 years ago? Well, like there is a statement that building better detectors is hard. Generally, the logic is that a better detector means that you have a lower bound on the frequency. A lower bound on the frequency means that you can study bigger black holes. And then bigger black holes means that you can probe black holes with more extremal mass ratios. Basically, bigger is better. Here is the logic. LIGO roughly probes a hectohertz or 10 to the second power. You can then convert that to the type, like using this equation roughly gives you the mass of the binary black hole system that you would study. It's roughly 50 solar masses then. This probes interesting physics. There's this pair instability that says that you shouldn't have black holes in roughly the 50 to 130 solar mass range. So you are probing interesting physics with LIGO. But then now we have future detectors, like future ground-based detectors are going to be probing 1 hertz range. So that's going to be 2 magnitudes more. So you're going to get 5,000 solar mass black holes. And then finally, you're going to have LISA, which is going to be a space-based detector, which will be probing 10 to the -3 hertz, which will be posing 5 to the 10 to the 6 solar mass black holes. And yeah.
So can you expand on why you say that the bigger the black holes are, the more interesting the physics? Because I would expect the opposite.
No, for quantum effects. But the statement is that when you have these bigger black holes, maybe bigger black holes isn't really the thing that I want to say here, but the ratios between the black hole masses, like to get there, you can probe a lot of interesting physics if you have a large mass ratio. If you have, for LIGO is not sensitive enough really to see like these mass ratios of black hole are roughly the same. But once we get to this like really big black holes, we can have one black hole that's like 50 solar masses, and another black hole that's like 10 to like 1,000 solar masses. But people will tell you different like reasonings for what's interesting. But basically you can, for these larger black holes, it is easier to study like the fine-tuned structure, like the exact, like the precise quasi-normal mode physics. But
for deviations of GR, that's going to be dark. No? I mean, for deviations of GR, I would expect that the smaller the black hole is, the more curvature is going to, the more intense the curvature is going to be at the level of the horizon.
Sorry, I think you're thinking the logic that you're coming from is extremal black holes, right? So you're saying like for extremal black holes, if I have a light extremal black hole, they can be quantum. Like if I have a black hole that's 0.998, I can show that for quantum effects to dominate, the black hole needs to be like roughly two Planck masses or something. Like it needs to be really, really small. But this is different intuition. Here we're probing classical physics. We're not probing. The logic here is that we're probing like classical physics. We're not probing like the quantum physics of near extremal black holes. But you are correct that like small black holes are also interesting and will be something that will be probed with other experiments in the near future. But for right now, I'm just talking about classical physics. The physics that will be probed in this experiment is, for example, if there's ultralight particles, they will significantly affect the in-spiral if you have small mass ratios. But that was a good question. Yeah, this experiment is not probing all the interesting physics. There are other experiments, but this is the one that is like the most famous. Okay, so there's lots of work to do. What is my immediate goal as a like postdoc theorist? My immediate goal is to calculate what the waveform is. So actually do a direct computation of the waveform. The way people do the waveform right now is that they usually calculate an intermediate object, for example, the binary Hamiltonian. And then they use the binary Hamiltonian to calculate the waveform, usually with some additional phenomenological model. So the question that we wanted to do was, I want to actually compute the waveform like directly in a semi-analytic procedure. I don't want to use numerics. I don't want to have like a phenomenological input. I want to actually have like a systematic expansion that I just have to plug into a computer and I can just do the integrals. And once I have the integrals, I have the waveform. This is useful.
Numerical or analytic, exact or numerical?
The goal here would be analytic. And the reason for that, I'll get to. I'll get to the why I'm going to say that in a minute. But this is really hard. Computing the waveform is extremely difficult. The problem is that you need to generate the waveform for very generic parameters. You need to generate it for generic masses, the generic spins of the black hole, what the trajectory is, what the energies or / velocities of the black hole. These like the waveform can vary dramatically depending what your input parameters are, like the parameter describing your in-spiral. The actual merger itself, like when the black holes coalesce, as I emphasized before, this is a strong field gravitational process. There's like, in a sense, there's no obvious perturbation parameter. You can't do a perturbative expansion in G. So you need simplifications. The simplification number one is, as I alluded to in the beginning, is I'm going to focus on the in-spiral phase. So the in-spiral phase, you actually have like a weak coupling parameter, like you can do, there exists a variety of weak coupling expansions, and it is computationally tractable to derive analytics during the in-spiral phase. The reason this is desirable is that, let's say I could just do, like you had your question before about numerical general relativity. In principle, like if I didn't have any limitation on computers, I could numerically simulate all of this. The problem is that it's very computationally intensive to do so. It's like extremely, like it's not feasible to just numerically evaluate every single waveform. You can evaluate the mergers, like if you know that a merger is happening, like you've seen that the in-spiral is occurring and you know that a merger is going to happen, or you know that there's a merger in your data and you just need to simulate it once, then yes, you can just do like you can do a simulation once, but you have to simulate it for, you have to do a simulation for basically each choice of parameters. So it's like, and each of these is like lots of lattice spacing. Yeah, but it's super high precision. If you do it, it's very good. The goal here is, I put pseudo analytic here. It's just, maybe it's not fully analytic, but at the very least, it's not as intensive as just doing numeric general relativity. The goal is to do a weak coupling expansion of some kind, either low velocity, small mass ratio, just something. And then
these masses of two black holes merging, that's the mass ratio?
Yeah, and just the ratio between
that could be small indeed, but velocity, how can you control velocity? So how can you have small velocity if they're merging? Is that
so you don't have a small velocity when they're actually merging, but far away from the merger, you could have small velocity.
Is that good enough for the calculation you're doing?
We don't do the small velocity expansion, but generically, yes, to a degree. There's actually some arguments that the small velocity expansion works significantly better than it has any right to be. I have read one paper that's entire thesis was that the small velocity expansion is basically better than it should be.
Intuitively, if two black holes merge, don't you inevitably get high velocities? Inevitably.
Yeah, during the merger. But the statement is before merger, when they're far away from each other.
Is that good enough to know what's happening far enough? I mean, in this physics, I mean, you don't worry. Don't you need to worry about small distance behavior?
Yeah, if I was worrying about the entire system, but again, I've done a simplification here where I'm focusing on the end spiral. So I'm saying for the actual merger, I'm just going to do numeric relativity for that, and I'll do black hole perturbation theory for the ring down. But for the end spiral, which is really important for like cycling through the data and like just trying to find when a merger is happening, it's important to have computationally cheap models for the end spiral.
I missed the meaning of in spiral. In the nutshell, what does it mean?
In spiral means before they've merged, so they're in spiraling towards each other. Yeah.
Okay.
So the goal here is I'm saying these like the merger has no obvious weak coupling limit. There's like that has no hope of doing any kind of analytic expression that I know of. So the merger is just dead unless someone has a significant breakthrough. The ring down, you can do black hole perturbation theory, so it's a little bit better. But the in spiral was the real regime where you can have analytic computational control. Because you have a weak coupling, which is either going to be the velocity, or you can also do a perturbation how far away the black holes are from each other. So right before they merge, like until they merge, they're like this is a pretty good perturbation.
The hardest part is the merger part, you say?
Yes, the merger, yeah, because it's fundamentally hard because it is strong. There's no weak coupling. Like as physicists, we are trained to take a complicated system, find an integrable limit, and then perturb a way around that limit. That there is not an obvious way to do that in the merger since it's purely strong field.
In the ring down, you still have a
In the ring down here, because it's just a highly excited black hole. You can just do like you have a single black hole and there's like excited modes around it, but it's still just black hole perturbation theory. You do an expansion in G. But this is not true. This is not obviously true for the merger. At least I don't know of one.
Sorry, what are the main techniques for calculating the end spiral at the moment then?
So that it ranges from who you talk to. There is the like direct calculations from general relativity. That's the paper I listed at the beginning. There's a multi-pole moment expansion is what they seem to be using or what they seem to favor, where they approximate the system in like some multi-pole moment and then like just solve the Einstein's equations iteratively. I am not an expert in that. So that's number one. So that's like what Demore uses. That is an expansion in small velocity. So you're solving Einstein's equations perturbatively, assuming that your black holes have small velocity. The second method that people use is something called the world line. So they say that these black holes, like they follow some kind of classical trajectory, and then you do perturbation theory around that trajectory. If the trajectory is classical, like a Bayes leading like a Bayes equations of motion in some limit, then you can do perturbation theory around that trajectory. Here they either do the post-Newtonian, they either do a small velocity expansion, or they attempt to do some like small mass ratio or something else. The next kind of perturbation is something called self-force, where they actually do this, they do an expansion small mass ratio. They have like the leading order in self-force is that you say that one of your black holes is just a massless particle, is like infinitely light compared to the black hole, and you're just doing like a particle that doesn't back react at all in a black hole background. And then you do perturbation theory on top of that, where you say it actually back reacts a little bit, and then it back reacts a little bit more, and then it back reacts a little bit more. The technique I'm going to be talking about this talk is the most closely related to the world line formalism. You can actually show they are equivalent. It's just different flavors of doing the same calculation. Did that answer your question?
Yeah, that's right.
And this is all for the in spiral phase. Yeah, again, merger, it's like merger is just, you just have to do numeric relativity to my knowledge. I don't know of any, like maybe someone will come and tell me that there's something that I haven't heard of, but to my knowledge, you just have to do numeric or general relativity. There's no kind of weak coupling. Well, some people have tried to do an expansion in 1 over space-time dimension, but I haven't really seen that work. Okay, as I was emphasizing before, the bound state physics is hard. Numeric relativity is the best, but it's computationally intensive. So you want these pseudo-analytic approaches that let you generate waveforms cheaply. So you don't. So if you're like, you have a space of data that you're looking at and you want to generate all possible waveforms that could match this data like very, very quickly. And this is why the weak coupling expansion, like you want some kind of weak coupling expansion here of the type that I was describing. Again, I would like to emphasize that usually all of these techniques that people have done focus on computing an intermediate object that they then use to calculate the waveform. For example, they calculate the effective Hamiltonian of the system, and then they use the effective Hamiltonian to calculate what the waveform is. But here I want to do a direct computation of the waveform. I don't want any intermediate steps. I want like an actual calculation that just gives me the waveform. And there's no kind of intermediate mumbo jumbo where something could go wrong. But the problem is still too complicated. Even in the bound case, doing the strategies that I've described are extremely complicated. Bound state physics in general is just hard. You can ask any QCD person. So instead of studying the bound state physics, I focus only on the in-spiral phase, and then 2, I pivot to studying the scattering waveform. So instead of studying black holes that are orbiting each other, I study black holes that will just go in, deflect off each other, and then go out. This is not the same as bound, but it's very, very closely related. For example, you can show that at low orders in perturbation theory, you can literally take the result that you derive in the scattering case and just analytically continue those functions to get the same case for the bound. So even though these are not the same, there's good reason to study this if you're just interested in the bound case. And in addition, it's just interesting physics by itself. The scattering waveform might itself have interesting physics independent of being related to the bound state problem. Yeah?
It's kind of showing a repulsion. Should it be like an attraction?
Yeah, this was just this, like, I don't even think these are black holes. I think I grabbed like gluons. All right, so as I said, we're switching from bound to unbound. We're switching to the unbound system. It's now just a scattering amplitudes problem. I have 2 black holes going in, I have 2 black holes going out, along with a bunch of gravitons. Also, in addition, the scattering waveform is pretty simple. So if I have the bound waveform, they're orbiting each other. It looks like this almost periodic function that's emitting radiation. In the scattering waveform, they just come in and they go out. It's just a blip. So it's computationally simpler. And then now, because I'm studying a scattering amplitudes problem, and I am trained in scattering amplitudes, I can apply all the scattering amplitudes technology from when I was in grad school. So the scattering amplitudes program is this program that basically says that scattering amplitudes appear in so many parts of physics, and they have interesting structure. It is interesting to just study scattering amplitudes independent of almost independent of the system in which you're studying them. Just scattering amplitudes themselves are like an interesting object and have enough structure to be worth studying. And just remembering from your QFT class, the way you compute a scattering amplitude is using Feynman diagrams. Like you write down all the diagrams, and then you write down the term corresponding to each diagram, and then you sum over all the diagrams.
But you said you ignore quantum mechanics here, so
Yep.
what are you?
Yeah. No, that's what this talk, you show that classical physics is encoded in higher loop scattering diagrams. That is what I'm going to show later in this talk. You often hear in QFT courses that higher loops is quantum. This is fundamentally incorrect. And I will get to that later.
The graviton will always be exchanged by something else. There are no external graviton particles in the diagram you showed us. Can you go back?
This one?
Yeah,
or this-
the Feynman diagram.
Oh, this was just an example.
Just an example.
Yeah, this is just an example.
Right, but in the ones you are gonna consider, don't you run into the usual problem of complexity when it comes to gravitational loops, you know?
Yes, yeah, we do.
Notorious.
Yeah, but this is what scattering amplitude program is nice for. Because the scattering amplitudes program, there's a book by my advisor that tells you very nicely how to do these kinds of computations without actually evaluating any Feynman diagrams.
Does your advisor make use of the technology developed by what I call the unitarity boys, you know, Zvi Byrne and company?
Yes, yeah, we use yes, that's right. I'm going to use generalized unitarity in this.
Oh, okay, very
Yeah.
good, thank you.
I don't actually I don't do any Feynman diagram perturbation theory beyond tree level.
Okay.
I construct an integram that you could get by summing higher loop Feynman diagrams, but I don't actually construct those explicitly. So the point here is that I'm going to, all of these things, I'm very happy you're saying these questions because it illustrates that this is a hard problem. But the reason why the scattering amplitudes program is nice and why this textbook is nice is that it shows you that these calculations are actually tractable. For example, if you do like a 5 gluon calculation at tree level, so you just compute 5 gluons coming, like 2 gluons coming in, 3 gluons coming out, and it's just a tree level computation. Maybe I should do 6 gluons. You can show that there's like thousands and thousands of diagrams. If you go, as you go to higher and higher point, the number of diagrams, I think, increases like factorially squared or something. You get thousands of diagrams. You don't even need to go to one loop. It's tree level. It's not even gravity. It's gluons. But you can show that the final answer has a closed form solution that's written in one line. At least for some particular sectors in D=4. This is an example of emergent structure that happens when studying scattering amplitudes that is very
Do you need MHV for that?
Yes, you need MHV for that, but there are still closed form solutions even for the non-MHV sector. You just can't write them in one line. So they're one page instead of a line, but that's still pretty good for something that literally takes arbitrarily number of diagrams to write down. I can write down a closed form expression. This kind of technology has been previous. We are not the first people to study scattering, to study classical gravity using scattering amplitudes. People have already done this for those intermediate observables I was talking about. So even if I'm not computing the waveform, I could compute the binding energy. So what is the energy contained in the system of the two black holes, or what is their scattering angle? Like what is the angle of deflection? These are observables that have been computed using the scattering amplitude techniques up to very high order. I'll tell you what this means later in the talk, but you can see that they get very, very close to numerical relativity. So the first order, it's pretty far away. This is scaling the impact parameter, and this is the scattering angle. First order is pretty far away. Second order, you get closer. Once you're getting to fourth order, which is state of the art, you're like almost on top of it. And then there's
Order in what?
it's going to be 1 over the impact parameter. It's the expansion.
That's your order?
Yes.
Okay.
And then here you can do this additional phenomenological resummation, which is called effective one body. And if you take as input, as you take as input these things, you can also get very close to numerical relativity. So there's a statement here that these kinds of techniques have been successful. You can see that they're getting very, very, very close to the actual result. And this is only after like 2 years. In 10 years, like the dedicated effort from a community, it's who knows where we'll be. But now I don't care about those intermediate observables for this talk. My goal is to compute the actual waveform. My goal is to say these two things are scattering off each other. I have a detector that is far away. What is the detector going to measure? The leading order scattering waveform was computed in the 1970s in these papers that I've listed here. Kip Thorne is on a lot of them, along with his co-authors here, Kovacs, Crowley, and that's it. And then you have another paper here that did the computation using Worldline. Jacobson, Mogul, Plepka, Steinhoff. And again, this is all the leading order computation. And then there was furthermore an amplitudes computation, which is analogous to the Worldline by Kauser, O'Connell, Gonzo, and Cristofelli. Waveforms from amplitudes. So these were all the leading order, like the tree level computation, so to speak. This talk is going to be the next order calculation. So the goal here is to compute the next order in perturbation theory to the scattering waveform, because there's fundamentally new phenomena that often appears when you go next order in perturbation theory. Leading order can only tell you so much. Oftentimes, maybe you don't want to go to like super duper high, like 17th order in loops or whatever, but there's often a fundamental difference between tree level and one loop calculations, which is exactly what we're going to see actually. There's fundamentally new physics when you go to one loop that is interesting. Again, to summarize my rationale for this entire computation, the goal is that we want to compute the analytic bound waveform. So I want to compute the bound waveform, and I want to compute that analytically. That is too hard. So I do simplification number 1, where I focused on the in-spiral phase when the black holes are far apart from each other and not touching. The problem is still too hard, so I did simplification number 2, where I'm studying now the scattering waveform. But eventually, the goal is to basically go back up here. Maybe you can't get the full analytic waveform, but at the very least, you could get the bound waveform. Additional motivation. It's better to you want to better understand classical phenomena in gravity. It's always useful. I'm going to list some results that are interesting there. Scattering waveforms are again by themselves possible targets for detectors. This is something I'm currently looking into. I don't really have that much to say. But it is possible that the statistics of scattering waveforms could be interesting. Like how often they see a scattering waveform, if they can actually measure it, might yield interesting physics. There are some deep questions you can ask, which is how is classical physics encoded in scattering amplitudes, which is I'm going to get to in a minute. How do you compute out of time ordered observables using scattering amplitude? So the thing I'm computing is not a scattering amplitude, but you can compute it using scattering amplitude techniques. And this object has deep structures, which have been explored in, for example, this recent paper, which shows that when you apply crossing symmetry beyond 4-point, you actually relate scattering amplitudes to out-of-time ordered observables. So the statement that everyone here is crossing symmetry at 4-point allows you to relate like something going in to something going out. Turns out that crossing symmetry at 5-point actually gives you observables that are not time ordered. So they're, again, just like deep question, like how do I study out-of-time ordered observables with amplitudes? Then finally, the final deep question is like, what makes gravity special? Gravity is a great theory, probably works up to the Planck scale. Like what makes this, makes this theory so fundamentally interesting? To summarize what the rest of the talk will be, what I'm going to show you is that the heavy mass expansion, so taking the black holes to be heavy, is equivalent to taking the classical limit. So I'm going to show that this heavy quark effective field theory limit of the theory is actually equivalent to the classical limit. I am then going to argue that the loop expansion is equivalent to doing a post-Minkowski expansion. So basically doing higher order corrections in 1 over impact parameter is what gives you a loop expansion, and that doing these loops computes classical corrections. And then finally, you can study soft limits of this expression. This corresponds to memory effects, things that could actually be measured by a detector in the near term.
The concept of loops providing classical corrections, it just sounds very kind of puzzling, right? At first.
Yeah, but there's one thing that you can kind of the thing that convinced me when I was first learning about this is that radiation reaction is a loop effect. So you can learn, like in Griffiths has a section on radiation.
Why call it classical? It's a loop effect, so quantum effect. Why?
It's not. Radiation reaction is not a loop effect. That is. I think most people would define radiation reaction. It's in Griffiths CNM, not in Griffiths quantum. And that if you write out that effect in terms of Feynman diagrams, it is a loop. It is a loop effect. But at the same time, it is not quantum. The way I define quantum here is the statement that I am working in the regime of large quantum numbers, or Bohr quantization. I'm saying that if I take my system and I take the quantum numbers to be large, that is what encodes classical physics. And I can do perturbation theory in those quantum numbers, and that is classical physics, and that is encoded in loop diagrams. If you want to argue that radiation reaction is a quantum effect, then yes, I agree that it's quantum, like what I'm doing is quantum, but I really don't. I don't think if you went up to an undergrad and asked them if they actually had read Griffith's quantum mechanics and asked them what radiation reaction was, like whatever that chapter is, and said, is this a quantum effect? I don't think they would say so. I think they would be like, what's quantum? Because most people take Griffith's ENM before quantum ENM. All right, so now I'm going to get, how do you compute expectation values from scattering amplitudes? So this first one is just going to be, the thing that I'm computing is not an amplitude, so how do I compute it using amplitude techniques? And then after that, I'll get to this classical limit question, which seems to be more what people are interested in. So just to remind people what my kinematic data is going to be, my kinematic data is that there's 2 black holes going in, 2 black holes going out, in addition to 1 graviton. Okay. I define all of my momentum to be outgoing for just convenience. That's how I was raised. There's no practical reason for that. It's just the way it is. And K is my outgoing momentum. Q is going to be the transferred momentum from my black holes. And then UI is like heavy, is the normalized form momentum of the black hole. So it's the normalized form momentum of this like black hole corresponding to P1, P4, and then there's another UI corresponding to P2, P3. How do I compute, before we go into how do I compute classical expectation values, we should review how do I actually do, what is scattering theory? Scattering theory is the statement that I define a scattering matrix, which is an operator that takes my system from t equals -infinity to t equals infinity. So when I take S acting on some in state, I'm going to get an out state. And then what you do in perturbation theory is you say this operator is equal to I, which is just the statement that nothing happens, which is what happens the majority of the time, plus this transfer matrix, which contains the non-trivial information of S. And when we were computing scattering amplitudes, we were computing matrix elements in T. As you can see, M out and N, out N, I'm just computing, I take a state, I evolve it from t-infinity to infinity, I get a coherent state, and then I take the inner product with that with a particular out state. And that gives me my amplitude, the probability that I will get out from N.
What is in prime?
What?
There is in prime.
Oh, there should be no prime there. That was a typo. Sorry. So how do I define, what am I actually computing here? It is not an amplitude. An amplitude in the sense quantum mechanical. The thing that I'm computing is an expectation value, fundamentally. I'm computing the expectation of an operator O, and I'm computing how it changes from t negative infinity to t infinity. So I'm taking the expectation value of the operator with the out state minus the expectation of the operator with the end state. This is just the statement of what my observable is from, like, this is how you define what the average like expectation of an operator is in quantum mechanics. But then now the trick is that I take that previous step where I took out is equal to S hat n, and then I substitute in S hat n equals I plus the transfer matrix. So I just take this expectation value, I write it in terms of the scattering matrix, and then I just substitute in this definition here. And all of these terms here, you can identify them with very basically just scattering amplitudes. Like they just involve one t hat. There's this O hat that's kind of weird, but these terms here are just scattering amplitudes. Like you can compute them with scattering amplitudes techniques. This last term is a little bit more weird, but it's also something that we can compute with using scattering amplitude techniques. You can really, the way that you can think of this is that for those of you that know NN perturbation theory, this computation is a version of that. So in NN perturbation theory, you're saying that I don't know what my out state is. I know what my in state is, and I am computing what I want. Given my in state, I am computing my out state. And you have to do all these Schwingish, Kaldish, contour manipulations, all of that stuff. But that has been absorbed into like just defining T and T dagger and S dagger in the previous slide. So if you don't know what NN is, this slide doesn't matter. But for those of you that do, what I have done is equivalent to that. So I mentioned that the first two terms that only had one T were just amplitudes. So you could just literally compute them the same way that you would normally compute amplitudes. You could give them to a normal, just a first year QFD grad student. The second term is a little bit more weird because it has two T's. So to evaluate this, what you do is that you insert an identity operator. So you insert an identity operator that sums over x's, which sums over all possible intermediate states. Graphically, you can represent it like this. So here I have two amplitudes, and I am summing over all possible intermediate states, and I'm integrating over their phase. This is equivalent to just taking usually a normal Feynman graph and just saying I have some propagators, like I have all the propagators that I've listed here, but these propagators are now cut. So when you do normal Feynman diagram perturbation theory, you have p squared minus m squared plus I epsilon. Here you're saying all of the propagators contained within these two blobs are still like I epsilon. I think this one is negative I epsilon because it's T dagger. But then these propagators are not I epsilon. They're just delta functions. Sorry, that's the slides were up. So here these were the normal propagators that you do a normal Feynman diagram perturbation theory, but when you insert those on-shell states that you're summing over, instead of inserting the normal propagator, you just insert the delta function. And the delta function corresponds to how this state is on-shell.
But normally what goes in the loop is off-shell. So why do you get away with on-shell condition?
Because the loop just comes from the fact that you're doing perturbation theory. Like you're just like perturbation theory just comes from like there are a bunch of diagrams contained within these blobs. And I can just sew them together with this like on-shell cut. There's no it's just it's fun. Like the statement here is that this is fundamentally not an amplitude. An amplitude would involve only having a single T. This is an amplitude. But this object that I'm computing is not an amplitude. You can relate it to an amplitude. It's like you take two amplitudes and then these are all on shell, and then you add in these propagators that you would have here, and then instead of them being off shell, you added delta functions. But this is not an amplitude. You can compute it the same way. You can apply the same techniques, but it is just fundamentally not an amplitude. Here I give a bit of a graphical description that I should have maybe done in the beginning. Again, T dagger T. I insert this identity over internal states. I get the sum, where I have the sum over all possible intermediate states in their phase space, and that gives me the graph that I was representing, the picture I was giving before. So what you roughly get is that the expectation value of observable, if you're doing KMOP, is an amplitude or a sum of amplitudes minus these cut objects, which are not amplitudes, but you can use the same computational techniques to evaluate them. This expression is exact. There's nothing about the classical limit here. All I've done is told you how to compute expectation values using S matrix perturbation theory. There's nothing classical has happened.
Why do we have the Fourier transform there?
Sorry, that was, I was gonna say here, yeah, that was a good. I have you additionally, what you do in the KMOC paper, is that you can just do without the Fourier transform, but generally you want to do a Fourier transform to impact parameter space as well. So you work in impact parameter space instead of working momentum space. You do the usual computation with amplitudes, and then you Fourier transform it to impact parameter space. Okay, so summary. Ignore this thing so far. The KMOC recipe is going to be like isolate the classical limit, which I haven't got to yet. I know I haven't got to it yet. You're going to subtract the set of cuts, which is what I mentioned before, and then you Fourier transform to impact parameter space. Now we get to the classical limit, so that will make a little bit more sense. So here, reminder for kinematic data. I have black holes. I have two black holes here. I have one black hole here, it's matter line. I have one black hole here, it's matter line. And I have the outgoing momentum K here. Here I'm going to give a little bit more detail again for the intuition that you should have is that the Q is the transferred momentum. So it's the momentum going this way and this way from your black hole P's. And then the U's again are the average core momentum. It's a P1 minus P4 here because I've done like everything is outgoing. If you flip this to be incoming, then it would be P1 plus P4. There should be a factor of 2 there. The classical limit corresponds to taking the impact parameter to be large. So before I mentioned the Fourier transform, this is why I mentioned it, is that the perturbation series we are going to do is that we are going to take the impact parameter to be large. A conjugate to taking the impact parameter to be large is to take the transferred momentum to be small. So what I do is I'm taking my B, I take the conjugate variable Q, and I take it to scale as H bar. In addition, I also take my outgoing radiation to scale with H bar, and I take my L, the L loop momentum that is running in the loop to also scale with H bar. In addition, I don't have a nice explanation for it right now, but you take kappa or square root of G to scale as square root of H as well. This is to get a consistent expansion. But really the intuition here is to derive this. You just say, I'm going to be working with B being large. B is my quantum number. It is the thing I'm taking to be large in Bohr quantization. And when I take it to be large, the leading order contribution is given by taking my integrand with these scalings, taking a series expansion to H bar and then integrating. How this affects perturbation theory is, for example, this is the kind of integrand that appears. I have L running in the loop. You can check that momentum is conserved. These terms here, these correspond to gravitons, and you can show that they have uniform H bar scaling, so they don't change when you do the series expansion. These matter lines do not have uniform H bar scaling, and you can show that when you do the H bar series expansion, they get converted to linear propagators. So what happens here is that when I'm taking the classical limit, I've given a justification of I want to compute my amplitude in the limit that B is large. That corresponds to taking these things to scale as H bar. So then I take my integrand and I just scale it with like these H bars I take to be small, and I just do a series expansion in H bar. And this is what the classical limit means from the perspective of scattering amplitude. I just take certain things to be small and I series expand in my integrand. And the way it changes perturbation theory for my graph is that it converts some of these matter propagators to linear propagators in this case. Maybe a little bit more detail is helpful here. So let's focus on tree level. At tree level, the 3-point doesn't really change very much. You just rewrite like your incoming and outgoing momentum in terms of U. At 4-point, there is a pretty dramatic change. This thing has full support on kinematic space, and you can show it has the desirable H bar scaling. But this term here, you can show does not have full support on kinematic space. And it actually has is the leading contribution in 1 over H bar. So this is called the superclassical term, and this is where this intuition should come from, that like amplitudes are intrinsically quantum. Like they don't actually, like when you're computing an amplitude, you're computing like a quantum mechanical object. And the way that it manifests is that when you take these limits, when you take the H bar to 0 limit, you get these terms which are superclassical, which are leading in 1 over H bar.
I'm confused. I see 1, 3, and then 1, 4. Are these two separate diagrams, or is it to get? Are these two separate tree diagrams you're discussing?
These are, yeah, this is one tree diagram, this is another tree diagram.
But our process involves four.
Yeah, sorry, I'm just focusing,
I'm focusing on one vertex.
I'm just focusing on this, I'm not going back to our, the full process that we're thinking of.
So, but I need to know the full picture so that I can see whether this is a tree diagram you're discussing or a loop diagram.
No, so my statement is that, here, if you compute, like, the tree diagram of the process that I want to compute is too complicated. So instead, I'm focusing on these graphs because they actually can be written out in a simple way. So the phenomenon I'm trying to focus on here is the statement that if you do the H bar expansion,
Mhm.
you're going to find that the leading contribution has has basically undesirable scaling in H bar. And my statement is that if you did loop corrections, like if I did this at higher order, at L loop, I would find that the leading order term scales as 1 over H bar to the L. So if I try to take, the point that I'm trying to make here is not really related to the process that I'm computing, but it is more the statement that if you take the classical limit and take H bar to be small, at L loop, you will naively find that like the L loop dominates over L minus 1 loop as H bar is going to be small. And
It's very counterintuitive, isn't it?
yes, it is very counterintuitive, but this is how it's manifesting that, again, like the classical limit doesn't really exist for an amplitude. Like an amplitude is intrinsically like quantum observable. So it makes sense that it doesn't really have a good series expansion in 1 over H bar. The difference here, the key magic is that when you actually compute KMOC, so you compute the thing I was studying before, the out of time ordered observable, you can show that all of those terms cancel among themselves. So you can show that even though the amplitude doesn't have a valid series expansion in H bar, that if I compute the L loop, I will have a 1 over H bar to the L approximately. The statement is that all of these super classical terms, which are undesirable and basically kill the fact that an amplitude doesn't have a good semi-classical limit, are killed when you actually do the computation for KMOC, when you're computing that like expectation value that I was describing before. And this is a key result. This is a statement that the classical limit doesn't really exist for the amplitude, but it does for expectation values. Like if I'm computing the expectation value in a coherent state, that has a classical limit. But
How do you explain magic cancellations? There must be a reason. Is
yeah,
there
so the reason
symmetry or something or?
no, it's not really symmetry. The statement is that you do a WKB like approximation. So you say, even though the S matrix doesn't have a good 1 over H bar approximation, the exponential of the S matrix does. So if I write the exponential as EI n hat, and I say that n hat does have a good series expansion to H bar, this is sufficient to show that the KMOC observable also has a good series expansion. It has a good series expansion H bar. But you can show that the S hat like does not, because like this n hat goes as 1 over H bar. So if I did a series expansion H bar of exponential 1 over H bar, like that's not a good series expansion. It's only the log of S that actually does have a good series expansion. And that is the thing that appears when you're computing these expectation values. So just to summarize that point, the goal here is I'm computing, I should have written this slide. I'm computing this object, the expectation value where I'm substituting in like S for T and I'm computing this whole thing here. And if I was just computing like this term or even this term, I would find that there's no real way I can take the H bar going to infinity limit. That just doesn't have a good limit if I'm computing these terms individually. But when I combine these terms together, I find that all of the 1 over H bar terms that are undesirable cancel among themselves. And this is a manifestation of the fact that there is a WKB approximation of the amplitude. That the amplitude, if you do the H bar, small H bar limit of the amplitude, you will get something that is like exponential 1 over H bar, not a series expansion H bar. And note that, again, exponential and 1 over H bar, like this does not have a good series expansion, because if you series expand this for H bar going to small, it's like a Lorentz series in both directions, so to speak. Okay, I have the last 10 minutes. And now I can do the actual part of the talk. So now we compute the waveform. So before, everything I said is completely general, and you can apply it in actually just complete generality. You don't need to think about classical gravity. This is something that you can do for like any kind of classical limit that you want to take. You want to compute an expectation value, you can use KMOC. And then if you want to take some particular classical limit, you find the quantum number that you're taking to be big or small, whichever one. And then you take your integrand and you do a series expansion in those in like whatever you're taking to be big and small. But then now we are applying this technique to classical gravity, and we are saying that the two things I've written before can be applied in the classical gravity regime. So what I do is I say the observable, the O that I'm going to compute, is going to be the waveform. Like you can compute it like an it's an R tensor thing. And what I do is I say H, I assume my metric takes the form G plus H, where it's weakly coupled at infinity and quantized. And I just take this definition of H and I just plug it into R, and I get this definition of R. And this is assuming that I'm working in the infinite space, like far away, like time infinity to negative infinity, where the theory is weakly coupled. And then if you go through the entire process I described before, you roughly get this Fourier. You have a Fourier transform in V, like I promised over here. And then in addition to that, you also have an integral over omega, which is the energy of the graviton. And this thing actually gives you the waveform. So after all of that, you can actually, in principle, do this computation yourself.
Quick question. So you did say that the scattering amplitude is inherently a quantum object, right?
Yeah.
And then you prescribed some procedure to take a classical limit to define it.
Yes.
And then, so what are you doing here with classical gravity? So
This statement is that the amplitude doesn't have a good classical limit, but the K-Mach observable does. So you take these linear combinations of amplitude-like things,
right,
and that does have a classical limit.
right, but there your starting point was some quantum field theory for which you are calculating.
Yes, that's right.
But here you're starting with a classical field theory, which is gravity, classical GR, right?
Oh, sure, but I can just quantize GR. Like GR is an effective field theory. I can just take GR and then you do G plus H, and then I take H to be like H is a quantum field.
I see.
Yeah, this is only valid up to the Planck scale, but it's a normal effective field theory. So I'm taking a fully quantum like GR, and I am systematically taking the classical limit to compute my and then I'm computing an observable using this K-Mach formalism.
Aidan, you have said that you take the metric to be G plus H. Have you only taken G to be Minkowski, or you have also played?
Yes, we take G to be Minkowski. We don't. I'm looking at another background, like in self-force thing, but for the purposes of this talk, the background is just Minkowski.
Kappa has come in because you're already doing eta plus kappa H, is that right? Or
Can you say that one more time?
the kappa that came in on the second?
Yes.
That's because you're doing eta plus kappa H?
Yes, yeah, that's right. Yeah. It's like G plus H schematically.
Yeah.
There are coefficients that I'm ignoring in that statement. Okay, yeah, here's the exact statement. Like I'm taking G to be Minkowski plus kappa squared m divided by, this is the spatial distance between these, like the scattering event and the detector schematically, and then here I'm doing the series expansion in H in terms of the impact parameter. So this is what I mean by the classical limit, is I am doing an expansion of the metric in terms of 1 over the impact parameter. At leading order, this is just the tree level process. At sub-leading order in V, this gives you a 1 loop process. Does this answer your question that you had before? About
It helps, thank you.
yes. Okay, so again, to really sketch the calculation here, if you really like cut it down to the discard all terms, all factors, whatever, you are computing an amplitude minus cut-like objects. You are then taking the Fourier transform and the transferred momentum, and then you're doing an integral of the energy of your external graviton to go from to get to the time domain. If you did not do the integral over omega, you would get the spectral waveform. And then now, in the last 3 minutes, I'm going to say we can use the amplitude toolbox to do this computation. This is very technical, but it's just the statement that this kind of calculation where I am computing amplitude-like things, like even if I was just computing the amplitude, these computations would be largely infeasible. Like the amplitude at 1 loop 5 point is just, you cannot compute that with Feynman diagrams in any kind of efficient manner. So you use tricks. Or not tricks, they're deeper than that, but these new computational techniques, such as generalized unitarity and integration by parts to compute them. So generalized unitarity is the statement that if I'm computing an integrand, one way I can compute the integrand is by studying the integrand on its poles. So an integrand has a bunch of different poles, which corresponds to when possible particles can go on shell. And if I take an integrand and I say all of these particles are on shell, so let's say I work in the limit that the loop momentum of takes these particles to be on shell, the integrand will factorize into like a tree level times tree level process. And you can do that like for all like different processes you can possibly imagine. And you can use this ansatz, the fact that on these poles, the integrand has to factor into tree level amplitudes to reconstruct the integrand using just the tree level amplitudes without ever using a higher loop Feynman diagram, or without ever referencing a higher loop Feynman diagram. You just use an ansatz that the integrand has to have this property on poles that it factorizes into trees. And this is sufficient to reconstruct the integrand without ever actually doing Feynman diagram perturbation theory. Except for the tree level bits. You do actually need to calculate the tree level Feynman diagrams. It's kind of annoying. I'm not going to go through the algorithm, but it's purely technical. It's existed for 15 years. It's very useful. The end result is you get a sum of functions. You get an integrand that is like a sum of functions like this. Where the A's here can take on generic integer values. You get like, I think 220 of them. In principle, you'd have to integrate all of them, but there's this magical program called FIRE, which tells you that all of these different integrals are linearly related to each other. And you can take this massive basis of integrals and you can derive linear relations to them, and it reduces it down to a basis of 5 integrals. So you take your integrand, you construct your integrand, you get this massive basis of integrals, and in principle, you'd have to evaluate each individual one. But then you do integration by parts, and you can show that there are linear relations among these functions. And when you apply all of these linear relations, you get down to a basis of 5 master integrals. These are one loop integrals are a solved problem, or 10 master integrals total. It's 5, but there's symmetry. One loop Feynman integrals are a solved problem. There exist closed form solutions for them. These ones all schematically evaluate to the form of A plus B times log C. They're just logs. They're kind of scary. They look really ugly. I just included one example over here. Like this is a particularly bad one. It looks disgusting, but if you really stare at it, you just realize it's A plus B times log C. And all it really boils down to is computing what A, B, and C are. And these are things you can just do with direct integration. In addition, the last thing I want to mention is that, can I go for 3 minutes over? Is that you can show that the amplitude or this thing that you're computing, this should be n minus cuts, actually is divergent. So there's an IR divergence. And you can show that this IR divergence exponentiates. So there's an IR divergence. The IR divergence goes, you can absorb it into an exponential. And you can show that this divergence, that when you're computing the amplitude, which seems really scary, can just be absorbed into time. And this is the benefit of working with the time domain waveform, is that the thing, like everyone tells you that these amplitudes are divergent, they're not actually well defined. That's not actually true. You just take the divergence, it exponentiates, and you can just absorb it into some other parameter that you don't care about. T is like the relative time at which we measure T does not matter. So shifting it by an infinite constant is completely irrelevant. Final step is you do the Fourier transform. We did it numerically. We also did some stuff in n equals 8 supergravity because simplified there. I'll just state the waveform in the last 2 minutes. The expression is not human readable by anyone. I don't think it's like really long. There's lots of spurious poles. So the statement is, what physics can we extract from it? Well, one thing that, again, just to remind you, we are computing this here. So we're computing the classical metric, and we're computing the correction at G times M divided by B squared. And then we also take the polarization vector to be this value. Generically, I was going to show a movie, but I don't think I have time now. We just numerically evaluated the waveform in the time domain, and we just have a movie. Like we have what you would actually measure the waveform to be at LIGO in principle in the subleading order. In addition, you can study like what is the physics behind the IR divergent phase, which is pretty interesting. This was discussed extensively in this paper here. The physics behind this IR divergent phase is that in D equals 4, gravity doesn't fall off fast enough to be weakly coupled at infinity. So if you take gravity, and you do amplitude calculations, you implicitly assume that your theory is weakly coupled at infinity. You assume a Fock space approximation, that you can just have particles that don't interact at infinity. This is not true in D equals 4. Gravity doesn't fall off fast enough for this to occur. However, the thing that does happen is that even though it is not weakly coupled at infinity, there is a sense in which it is still trivially solvable. And what this leads to is the fact that even though there is a divergence when you're computing the amplitude, the divergence can be resummed into a universal phase that can then be discarded. So either is a statement here, like this thing, this higher divergence is interesting because even though it corresponds to how we are basically using an assumption that is not actually true, it is like basically true enough that we can,
It's similar to what happens in QCD.
yes.
Okay.
You can also, I'll just list that you can do something with the memory effect here. So memory effect is the statement that if I have radiation and I have a detector that are like some distance apart, after the radiation passes, they'll be displaced by a permanent amount. And you can relate this to the soft limit of our expression. So the limit, and if you take the omega to 0 limit, you can do the algebra that I've listed here. And you can show that relates to the soft limit, and we have explicitly computed the soft limit. And we've matched some calculations from Choksan and Sahu. And the expression matches. We also are doing the subleading memory terms and showing that those match as well. Conclusion, again, what we've done here is we're computing the scattering waveform in the classical limit as an expansion of 1 over the impact parameter. The leading order calculation is just a tree level calculation that was done first in the 1970s. We are among the first people to do the subleading correction to that in 1 over B. We did so in GR and n equals 8 supergravity, and we did so using this K-mop formalism where we combine this way to compute expectation values with the amplitudes and also like taking the classical limit of amplitudes. After we numerically evaluate the Fourier transform to time domains. So that's why I said pseudo-numeric in the beginning, is that we do the integrals that are like contain the non-trivial physics, but then we actually needed to do we numerically evaluated the integral to get the time domain expression, but it's not very hard. Like we have an explicit movie. And we confirmed some previous conjectures regarding the universality of the memory effect and subleading memory effects. New stuff to do is that I then came up like procedure for the bound waveform. I really emphasized that problem in the beginning. The physics that LIGO cares about is not unbound, it's bound. That's the things that they are measuring. So trying to find some kind of way to use scattering amplitude techniques for the bound state waveform is the biggest open problem. Other things you can attempt to do, one thing I'm doing is attempting to find resummations and other kinematic limits. So for example, we're taking expansion of 1 over B. If you take the mass ratio of the black holes to be very small, it's possible that you then can do an additional resummation that lets you get something that's very accurate. Formally, better understand this WKB approximation of the amplitude. So again, this ties into like the how classical limit emerges from amplitudes. And then maybe do this thing at higher loops and incorporate effects that I have ignored that would not appear until higher order in perturbation theory. That's it.